All right, let's jump right in. We hear so much about the magic of AI, right? But today, we're going to pull back the curtain. We're moving past the theory and into the real world to really understand AI engineering, what it actually takes to get an AI model out of the lab and into a real product that millions of people can use. And I want to kick things off with this quote from Google's Peter Norvig, because it just shatters the biggest myth in AI. Most of us think AI is all about these genius, super complex algorithms. But as you're about to see, it's just a tiny piece of the pie. So, if the world's best AI systems aren't just about better algorithms, then what is the secret sauce? What does it really take to build and ship AI that works in the real world? And boom, here's the reality check. Look at this. In a real live AI system, the machine learning algorithm, that's maybe 10% of the whole deal. The huge majority of the work, we're talking the real heavy lifting, is in data engineering, building rock-solid infrastructure, and just constant monitoring. It's a whole ecosystem, from the user interface all the way down to the hardware. And that brings us to something absolutely crucial about AI engineering. See, it's not a one-and-done kind of thing. You don't just build a model, high five, and walk away. Nope, it's a circle, a never-ending loop of getting better. So let's walk through that loop step by step. First, you've got to scope out the business problem. Then comes the really tough part, data engineering. Then you get to the cool part, model development. That's where the algorithm actually lives. After that, you deploy it out into the wild, where you have to constantly monitor it. And finally, you analyze its impact on the business. And, you guessed it, all that info feeds right back into step one, and the whole cycle just starts over. So, what's the difference between some cool experiment and an AI you can actually count on? Well, it really comes down to these four things. 1. Reliability. It has to work, even when stuff goes wrong. 2. Scalability. It has to handle 10 users just as well as it handles 10 million. 3. Maintainability. Your whole team needs to be able to work on it without, setting everything on fire. And finally, adaptability. It's got to change and evolve because the world and your data is always changing. All right, now let's talk about the real MVP, the single most important part of any AI system, the data. Seriously, in the real world, if you want to make your system better, forget tweaking the algorithm for a while. Focusing on your data quality in your pipelines, that's where you'll get the biggest bang for your buck, every single time. So where does all this data even come from? Well, you've got a few main sources. You've got your clean, structured system logs, stuff your own apps create. Then there's user behavior data. Things like clicks, what people buy, and here, obviously, privacy is a massive deal. And finally, you might have third-party data that you actually buy from other companies, which, let me tell you, often comes with its own headaches. Now, this is where it gets interesting, how you actually store all that data. It's a classic trade-off. On one hand, you have text formats like JSON and CSV. Super simple, easy for a human to pop open and read. But on the other hand, you have binary formats like Parquet and Avro. These are way more efficient for machines. To give you an idea, a 14 megabyte CSV file can shrink down to just 6 megabytes as a Parquet file. Now that might not sound like much, but when you're dealing with terabytes of data, that's a game changer. And it's not just about how you store it. It's about how it moves. Think of it like this. Batch processing is like reading a whole history book at once. You process these huge chunks of old data, maybe overnight. It's perfect for training a model on everything that's happened in the past. But stream processing, that's like reading a live news ticker. It handles data as it happens, right now. It's what you need for real-time features, like how many delivery drivers are free this very second. Okay, so you've got amazing data. Fantastic. But if you ask it the wrong question, you're going to get a perfectly accurate but totally useless answer. And this gets us to what we call problem framing. Honestly, this is half the battle in machine learning. It's all about translating a vague business idea into a specific question an AI can actually solve. Let me give you a classic example. Your boss comes to you and says, "We need to speed up customer service." Okay, what does that even mean for an AI? That's a business goal. A great AI engineer takes that and reframes it into something concrete, like, let's build a model that predicts which of these 4 categories a customer email belongs to. See? Now you have a clear task. You can define your inputs, your outputs, and exactly what you're trying to optimize. And how you frame that problem has massive consequences. Imagine you're building an app store recommendation engine. The slow, clunky way would be to try and predict a probability for every single app in the store for each user. That's super slow, and what happens when a new app gets added? Your whole model breaks. But check out the smarter way. Treat it as a regression problem. For any given user and app pair, just predict a single likelihood score. It's way faster, it's flexible, and it scales like a dream. So we've got our data, we've framed our problem. Now, finally, we can talk about the model. But here's the dirty little secret of AI engineering. There is no such thing as the best model. It's all about the art of the trade-off. It's about finding the best fit for the job you're trying to do. And this little matrix here, this shows you the fundamental dilemma you're always facing. You could go with a super complex neural network. Yeah, you'll probably get higher accuracy, but it's a black box. Good luck explaining to your boss why it made a certain decision. Plus, it's slow. On the other hand, a simple model, like logistic regression, it's not as accurate, but it's lightning fast, and you can explain its logic easily. So you have to ask yourself, what do we really care about here? Accuracy, being able to explain it, or speed? So what do you do when those goals are fighting each other? The product team is screaming for speed, but the ML team wants perfect accuracy. Well, here's a pro tip. Decouple them. Don't try to solve both problems with one model. Instead, you can build two separate models, one optimized for speed, one for quality, and then find a smart way to blend their results. This gives you way more flexibility to find that perfect balance. And that really brings us to the big takeaway here. Building AI that works in the real world, it's just so much more than the algorithm. It's the data, it's the infrastructure, it's the whole blueprint that ties everything together. So as we look ahead to what's next in AI, I'll leave you with this question. What's really going to matter more? A slightly better algorithm or a fundamentally better blueprint?